Hi, everyone, and thanks for joining us for another BactoSense in Action webinar. I'm Carl, and once again, I'm joined by my colleague, Kevin. Let's get started. Here's a quick summary of what we'll cover today. First, I'll walk you through the application we're focusing on, which is chlorine disinfection, with an overview of the process, some of the common challenges, and how the BactoSense fits in. Then I'll go into the application in more detail. So looking at where and how the BactoSense can be used to support this process. And finally, Kevin will share some real data examples so we can see what's happening in the field. Let's get started with a quick overview of chlorine disinfection. Chlorine disinfection is one of the most widely used methods for controlling microorganisms in water. It works by penetrating bacterial cell walls and disrupting essential processes. So that's like enzyme function and DNA, ultimately inactivating or killing the cells. There are a few different ways to apply chlorine. So you have sodium hypochlorite. This is quite easy to store and handle, and sometimes more common for smaller or medium-sized sites. You also get chlorine gas. This is highly concentrated and can be cost-effective for large-scale plants, but it does require some strict safety measures. You also get chloramination, and this is by combining chlorine and ammonia. And this forms chloramine, which is slower acting, but can last much longer. So it's quite ideal for sort of maintaining a residual throughout long pipelines and storage tanks or reservoirs. The choice depends on various factors like plant size, safety considerations, infrastructure condition, distribution distance, and also whether the goal is to rapidly kill on site or for more ongoing protection in the network. Chlorine disinfection is used across a wide range of industries. In utilities, it's a critical barrier in drinking water treatment plants and distribution networks to protect public health. It's also used in water reuse schemes, cooling towers, and wastewater treatment. And that's more to maybe control the pathogens before discharge or before reuse. In industrial sectors like food and beverage, pharmaceuticals, cosmetics, and maybe semiconductor manufacturing, chlorine disinfection can also play a key role in keeping processed water clean and safe. It's even found in desalination plants, manufacturing facilities, and other specialist applications where microbiological control is essential. So while chlorine is a powerful and versatile disinfection, it does also have its challenges, and that's what we'll look into in the next slide. So chlorine disinfection systems are powerful chemical treatment steps that inactivate microorganisms and are essential for producing high-quality, safe water. Other methods like UV and ozone are also widely used, but today we're going to focus more on chlorine. Like any process, chlorine disinfection does have its challenges, as mentioned. So overdosing can lead to unnecessary chemical costs. You might have equipment wear, you might also have infrastructure damage, and also the formation of harmful disinfection byproducts. However, on the other hand, you might have underdosing. So you have increases in microbiological risk, which can lead to financial and reputational consequences if indicator organisms are detected. Operators have to try and deal with these variable conditions. So changes in feed water quality, for example, changes in temperature throughout different seasons, or maybe changes in upstream processes. And at the end of this, they have to ask how much is enough right now. Unfortunately, standard microbiological tests can't always answer that question in real time. And that's where things like flow cytometry can add a lot more value. So to highlight some of these limitations, here's an extract from a paper by Chiswick et al. It explains that relying solely on these indicator species can be difficult after chlorination because counts are often very low. So this limits the detection through culture-based methods, and it can increase the error. To add, Indicators like coliforms, E. coli, and enterococci are highly sensitive to chlorine, but other microorganisms with greater resistance may still persist undetected. So using rapid automated flow cytometry alongside these traditional plating methods can be a powerful complementary approach. So this will help operators proactively manage the chlorination process. This is where flow cytometry and the BactoSense can make a big difference. BactoSense automates the process, providing rapid, high-resolution microbial data, and it also enables operators to respond instantly to abnormal changes. The BactoSense and flow cytometry in general delivers results at a single cell resolution and filters out any interference from non-bacterial particles. Using an ICC cartridge, for example, operators can get a true unbiased picture of chlorine disinfection performance, and from there they can make confident data-driven process adjustments. Now let's look at the ways the BactoSense can be applied in chlorine disinfection and the value it can bring. So first, we're looking at treatment barrier monitoring. So this is continuously verifying the effectiveness of the chlorination step and detecting any treatment failures or drops in performance immediately. Second, you can have process optimization. So fine-tuning the chlorine dosing and contact time to reduce chemical use and limit this byproduct formation. It can also help assess the impact of upstream events, such as filter backwashes or changes in raw water quality on treated water. On the right, you can see two BactoSense measurements taken before and after chlorine disinfection. Before chlorination, which is the dot plot on the top, ICC counts are around 260,000 cells per milliliter, with a clear cluster of cells visible within the gating. After chlorination, which is the dot plot on the bottom, you can see that this drops dramatically to about 750 cells per milliliter. So this is a clear indication that the process is performing very effectively in reducing cells. If you were to see a large cluster post-chlorination, this might indicate that there's an issue in your process. BactoSense can also help qualify and troubleshoot assets. By monitoring both the inlet and the outlet simultaneously, you can calculate the log reduction values in real time and clearly see disinfection performance. On the right, there are two graphs from the paper by Chiswick et al. The graphs show that HPC results might show 0 CFUs at the outlet, but intact cells can still be present. So treated water isn't always sterile. BactoSense is also valuable when commissioning new disinfection systems, testing new dosing strategies, or during maintenance to ensure that the chlorine barrier remains effective. Monitoring upstream before chlorination can also give insights into the microbial dynamics and also help optimize dosing. For example, backwash cycles or backwash events can be tracked in the data to check if chlorination remains effective. On the right, we can see a graph showing BactoSense data after one of these GAC filters. You can see there's a clear increase in cells per milliliter following a GAC backwash. With this information, operators can then closely monitor the chlorination step after such events and check whether they have a significant impact on the disinfection performance. And then if needed, adjustments can be made to improve the process, eventually shifting to a more predictive approach rather than reactive. Downstream in the network, BactoSense can also identify the regrowth potential in pipes, tanks, or even reservoirs, which can then be used to optimize chlorine residual levels. In summary, BactoSense is a powerful tool for chlorine disinfection, not only to detect these abnormal changes and give early warnings, but also to optimize process and better understand it. With this data, operators can then shift from reactive management to proactive and can even start taking a more predictive control. All right, well, that wraps up my section. I'll now hand over to Kevin, who will share some data and real-world examples from the field. Thank you.
Thank you, Carl, for this first overview in the first part about disinfection monitoring with the BactoSense and flow cytometry in general. Now we would like to focus a little bit more on some key findings and data overview that we have on the multiple projects with BactoSense over Europe and the world. So let's start with France, with the definition of a closed-loop water system in CSTB in France. CSTB has a pilot there that helps companies to develop solutions for biofilm monitoring and biofilm disinfection. And we've made some tests there over a few weeks to check if we were able to monitor the disinfection and what would be the results of that. So this test was during 3 different periods of time. First, we were heating the loop up to 37 degrees that you can see over there. Then we had a chlorine disinfection of 1 milligram of chlorine. The setup was done over a 3 period of time, clearly distinguished. The first was just heating in the water inside the loop from 22 degrees up to 37 degrees. Here we can see already it's a logarithmic scale, so of course it looks a little bit flat, but in the end it's starting from around 100,000 cells up to almost 1 million cells, which is kind of already a log increase. Then we had an injection of 1 milligram per liter of chlorine that will kill all the cells, and then we will just let the regrowth happening over a few days. And we can see, as expected, a regrowth that will be even higher than what we have before the shock disinfection. Now we are like almost 2 to 3 million cells. So first main findings we had is that, of course, if you manage and you increase your temperature, you have more bacteria in your system over time that will develop and create potential problems like Legionella or other parameters. The second key finding is that disinfection can reduce the ICC, the number of cells, from up to 4 logs. At the end, we were close to between 10 to 100 cells for the lowest results we had, which is kind of close to sterile water. At least from our perspective. And after 1.5 days, we will get back to more than 2 million cells, like I said. And all along the process, the dynamic systems was similar from what we can expect from an HPC and standard methods, which shows that it's really what's going on there. And then it can give a multiple implication beyond that, meaning that, of course, as we already know, that temperature and the nutrients and the warm water inside the system can lead to more bacteria and more risk. And the shocking effect is that just disinfection for a short period of time may create more risk than disturb, as you will create in the end more bacteria over time. And we have really nice details and show on the next slides, where you can see the first steps of the heating loop, where you can see the growth, especially in the HNA parts, which is the bacteria that have the more nucleic acid inside and that are more potential to growth. So over time, we have more and more bacteria in there, up to almost 1 million. There we have the chlorination step, where you could see all the damaged cells that will move and migrate outside of the gating of the flow cytometry, and almost nothing left. And then the regrowth, where the dead bacteria will kind of be food for the new bacteria, and they will grow and grow even more, kind of invaded and provide even more bacteria than before. Another case study linked to the one before, which was more like academic and first step, was done in the UK, where it's one of the main applications with the BactoSense is to monitor the effectiveness of the chlorination before and after a contactant, and to know if the chlorine injection is at the right level, and optimize also, of course, the cost of this. So the basic setup is 2 BactoSense setup, one before the contactant and one after the contactant. They will measure online in this total to calculate the log reduction of the intact cells counts, but also it will be able then for the operator to optimize the dosing of the chlorine and also optimize the contactant given the flow rate. There's an alarm threshold that will also be set up on the second BactoSense, so it can be used for the operator to know if something is going wrong, if the chlorine injection has a problem, or if there's something going wrong. And then they can discharge the water or treat it better, and so they can prevent risk and provide contaminated water to the customers. The idea of measuring also the pre-contacting is helping to know exactly the quality variation at the beginning of the flow before the contacting, and then it will help to know if they can adapt the chlorine injection depending on how much they need it at the beginning, because most of the times now about chlorine disinfection, they will more trigger around 0.3, 0.5 milligram per liter of chlorine in the water to assess and be sure that there will be always free chlorine in the water. So there's no risk inside the plant and in the network up to the customers. But most of the time it's more than what is really needed. And with this technology and with this setup, you could have a final monitoring of what's going on and chlorine when it's really needed, and be sure always that your water provided is safe to the customer. Following up that, we have now with monitoring the chlorine disinfection tank, but now we are also moving to monitoring chlorine up until the network. This is a case done in France in another water utilities that set up the BactoSense at the outlet of their drinking water plant, but also in a reservoir 10 kilometers down the pipes. And the idea was to monitor, okay, what was the effect of the chlorine disinfection all along the network, and if there were some key insights that we could have from this setup. The other idea was to compare these results with standard parameters, physical-chemical parameters that are used in drinking water, like turbidity and free chlorine, also a little bit of pH that is not shown there, but was also compared. So as I said, the setup was one BactoSense in the drinking water outlet, and then one BactoSense in the reservoir, and monitoring over time. First few insights that were shown was that, as you can see, the values of intact cells at the drinking water outlet where it was set up are higher than the ones in the reservoir, and the dynamics are smooth in there, that you don't see as much of variation there. It's because it's less sensitive to flow rate. Chlorine disinfection is fully done there at that moment, meaning that, yeah, you've got almost no bacteria anymore at the reservoir, while you can still have a little bit there. And you have a few log reduction there still going on, a reduction of ICC, because over time you get more and more bacteria damage. This is one of the main insights, that then, yeah, disinfection is still occurring and moving forward inside the network, and meaning that maybe even some spikes that we can see here. The first insights we can see from this application is that, firstly, on the drinking water outlet, and it wasn't shown with any other parameters, is that there's two baselines, two operating modes for bacteria and the dynamics, one over the day and one over the night. During the day, the value will be quite low, while over the night, the value will be higher. They will add the same quantity of chlorine between both. The main difference is the flow rate, because to save some cost on energy, they will mostly provide and use a higher flow rate during the night, because energy will cost less, and they will try to fill up their reservoir all along their system during the night. It will be more than enough to provide enough water to the people in the area. So as the flow rate is more important, there's less time in the contacting for the disinfection, and then the disinfection is still ongoing in the network. That's why even at the beginning we have a few thousand cells at the outlet of the drinking water. We have almost nothing in the reservoir. Still, we can see some spikes that we can see also on the drinking water, and this is linked more to pump starting and the variation that can link, as there can be some stagnant water and you can have some spikes, and then it will go back to the results before. But this is also something that that was unknown to them, and really interesting to optimize and prevent any risk linked to that. What we have from there is that if we compare to other standard physical-chemical parameters, we were able to show way more data, way more dynamics and info insights compared to the other. Especially if you compare firstly with turbidity, you can see it was pretty flat over the day, because it's drinking water, it's mostly regulated, and there's no correlation in the end. There's no comparison. If there's turbidity in your water, it doesn't mean that there's bacteria, and the other way around. It doesn't mean that if you don't have turbidity, you don't have any bacteria in your water. That's something that's especially on water, raw water, people will tend to make a short comparison to that. But in the end, you really need to monitor that quite closely with a dedicated monitoring instrument. Compared to the free chlorine method, that is the most and widely used to be sure that you provide a good and safe water to your system, we can see that the use spikes, they're kind of represent and they kind of depict the spikes by a consumption of free chlorine in the water, that it's normal, but still there's a lot of dynamic, as they are always trying to get to the 0.5 milligram per liter, which is their threshold. We won't see all the dynamics, we won't see all these different effects that can be seen with the BactoSense, and it can help also to optimize this chlorine disinfection. They are trying to set up to a 0.5 threshold because it's not regulated needed, but because they want to be safe. But in the end, given the results, given what we see at the end of the reservoir with almost no bacteria, you could say that, okay, maybe we can reduce the number of the quantity of chlorine you use and then save cost. Maybe also optimize your process over the night and smooth a little bit the flow rate change, so you don't have these two different baseline, and it will also help to reduce the amount of chlorine you can use. And with the BactoSense, you will be sure anyway that your water is safe, as you will see if something is going really wrong. And finally, the last case, which is starting from really the basic, just monitoring disinfection in a loop system, then in a tank, then also in the network. We have the full implemented solution in Switzerland, in Saxion, with our partner Pmax, that set up a full system, online monitoring and alerting, also using weathercast data that will help optimizing chlorination when it's needed and when it's not, as it's Alpine spring water there. The quality of the water is always nice and doesn't need a lot of treatment, so chlorination is mostly done to prevent any risk when it's raining or when there's some external environmental risk. It's coming back from some few incidents there in the process, as they don't have a lot of treatment. They're most sensitive to hygiene risk of their water. So they set up 2 BactoSense in their 2 main reservoirs in Saxion, and the idea was to monitor online the microbiology levels and define 3 different thresholds. One will be good water quality, the other one will be deteriorating water quality, and the last one will be bad water quality. Once it's done, they will also use the weather data that can have an impact on online monitoring. If they know that it will rain, or it is raining, it will send a signal to the BactoSense that will monitor and more closely the data and the microbiology levels. Rather than measuring every 4 hours, they will measure every 30 minutes, so they can have a close monitoring when it's needed, and on the other time it will just be there to be sure that everything is fine. And depending on the results, if we go to orange or red level, it will imply different action from the system that will either first start to chlorine at a higher level. It will also send alerts to the operator, so they know they can also prevent people from taking the water and alert them that there may be some risk in the water if it's really too bad. And they can also activate alternate supply that will be safe and will be monitored and discharge the main water that won't be used to prevent any risk, any contamination for the population. And then we use this technology with the compliance and the mixing of the BactoSense and some tools, data tools, and some automatization. They have now something in water that is always safe and mostly chlorine free, which is a really good plus for the population that can really enjoy the pure taste of the Alpine spring water. And so now I would like to thank you everyone involving in this webinar, and we can go up to the question. If you have any, you can feel free to ask him in the chat, and we try to answer as much as possible. Thank you very much.